Hello, my name is Patel, and my project is using electrostatic simulations to model ion engines to help predict maximum output velocity. Ion engines are a type of electric propulsion device. They're commonly used on space probes. Some examples are Deep Space One and Dawn. They produce a thrust by ionizing xenon gas, which is chemically inert, and they are accelerated by an electric grid after being bombarded with electrons from an electron gun. These ions are accelerated out in an ion beam and recombined with electrons outside so that the ions don't come back to the craft. There has been some development on Earth that utilizes those similar principles, but instead they ionize the surrounding air due to the high electric field created between two electrodes. Those ions are then accelerated by that said electric field and create an air current. MIT back in 2018 created a glider that uses ion propulsion. If we can improve this technology to be used for other applications, we can decrease sound pollution since ion propulsion is much quieter than, say, a jet engine, and reduce gas emissions in the air. However, ion engines may be efficient and have benefits to the environment, but they produce a very low thrust, and which is why we need to research them in order to increase their thrust output. My solution is to create a simulation in order to identify what design would be the best for Earth applications. In order to test it, I will create a simulation of a copper wire and a copper tube and see how those simulated results compare with real-world data by comparing them with an actual real-world experiment. I have two designs. One is my real-world design, and one is my simulation design. The real-world design works by an DC power supply plugged into an outlet that outputs 19 volts and 0.28 amps. And the positive and negative ends are connected to a voltage multiplier. The positive end is connected to a copper wire, and the negative end is connected to a copper tube. This is where we will create our ion engine in real world using different copper tubes later explained. In the simulation, we have two cylinders of different diameters and lengths. The small cylinder represents the copper wire, and the big cylinder represents the copper tube. Due to conductors having their electrons located on the surface, we can simulate a tube and a wire as two cylindrical shells. So the positive tube is the wire, and the negative is the copper tube. The blue sections represent where most of the charge is located and what is assumed to be held all of the charge. Due to the high edge effect created by the system, we can assume that most of the charge is there, and we will calculate the charge densities on each of them using their electric potential and the fact that the charges on them is equal and opposite since the diagram in the real world system is how that would work. So there are some forces that are significant to an electrohydrodynamic system, but in my simulation that will not be considered. So some important factors to include in this is fluid dynamics. This is a very important must, and you can use Navier-Stokes equations in order to model it. However, in my simulation, I will be only modeling a single particle since it is outside the scope of this project. We want to see how well an electrostatic simulation alone predicts it, so we will not be including some of these like fluid dynamics. While it is very important, it will be considered in maybe future works, it will not be here. Electric forces include the Coulomb forces, which will be considered in the simulation, are technically not the only electric forces that can be affecting a fluid, but since we are only modeling a single particle, that will not be necessary. Lastly, ion production is very important through coronate discharge. Coronate discharge, there are many types, and here we will be considering just that single particle, so that will always be there and not dependent on whether or not it was created. So We will also be including calculating approximate surface charges, as stated before, using some mathematical ideas. And lastly, we will be outputting trends, not exact velocity values, but because we will be scaling down the force values. Due to this, we will only see how the values compare with themselves. So some value in the simulation compares to a different value from the simulation. Here we have our Coulomb's law for 2D surfaces. Over on the left is Coulomb's law for 2-point charges. So this is the electric field. And here we have our kq over our position vector r to the power of 3's magnitude multiplied by the position vector r. Over on the right is the electric field strength of a 2D surface described by parametric equations. So here we have a double integral that is dependent with respect to u and v, which are the parameters of a 2D surface parametric equation. On the denominator is the equivalent to our position vector away to the power of 3. Here we have our x, y, and z parametric equations described in the parametric equations, and our d represents our parametric bounds, so our u and v bounds. There is a whole derivation in my paper which will describe this in further detail. We also will have to calculate the approximate surface charges. Due to the high edge effect, we assume that the majority of the charge is built up there. To find the total charge values, we can calculate the charge densities. So we can, using the fact that the conductor's charge is equal and opposite, so between the wire there's some positive charge, and on the copper tube there's a negative charge that is equal in magnitude. And we can use the fact that their electric potential difference is 20,000 volts. That is due to the voltage multiplier stated to have a 20,000 volt output. So using that fact, we can calculate the charge densities using a system of equations. Below are the electric potential values, the electric potential equations of each of the wire and tube. So the first one is the electric potential of the wire, and sigma W is the charge density of the wire, and electric potential of the tube is described in the second equation, and we will solve for the sigma T, which is the surface charge density of the tube. Now here we have a demonstration of our particle of the simulation. So it starts at the beginning and next to the wire, because that's where it will be simulated, because that's where it will be produced, and it will pass through the tube and accelerated eventually, and then it will pass through, and when it will get to 3 centimeters away from the copper tube, it will stop, and 2 values will be recorded: the max velocity that would be near the wire, and a final velocity where it is located now. Now back to our real-world experimentation. So we want to compare our results with our simulation, and we will be doing that in this. So we have 3 velocity values were measured for each system. In total, there are 27 different systems. The systems are dependent on the tubes and the separation distances between the wire and the copper tube. There are 9 different copper tubes, 3 different lengths and 3 different diameters, creating a total of 9 different tubes. There are also 3 separation distances of 1.5 centimeters, 3 centimeters, and 4.5 centimeters. The separation distance is the distance between the tip of the wire and the edge of the tube closest to the wire. On the right, we see that the anemometer in the background here is measuring velocity values at the center, between the middle and the edge, and at the edge itself. So we will measure those and average for each system what the average output of it is. and the input voltage, as stated before, was 19 volts at around 0.2 amps. Now, our results of the real-world simulation shows that the fastest one was the system with a tube of 2.6 centimeter diameter and 3.7 centimeters long, with a spacing of 1.5 centimeters between the wire and the tube. However, our simulated data predicted that the system with 2.6 centimeter diameter, but with the 8.6 centimeter long and 4.5 centimeter separation distance, was the fastest. So this shows that our data between the two different systems do not match. Now, there are a couple reasons why this doesn't work. But first, there are some trends that each of them have, and only one matches. So the real-world data has 3, and those are: the larger the separation, the slower the air current; the larger the diameter of the tube, the slower the air current; and lastly, the larger the tube length, the slower that the air is as well. However, there are a couple reasons why the simulation data trends are: the larger the separation distance, the faster the particle; the larger the diameter of the tube, the slower; and the larger the tube, the faster the particle was. So this was due to the particle being under ideal conditions with no viscosity and no resistance forces. In real-world applications, the further the particle would travel, the more air drag would affect it, and thus it would be at a slower velocity. Since this was not considered in my simulation, it was under ideal conditions and was at a constant velocity whenever no forces were acting on it. So, some future work is to include fluid dynamics and explore how Navier-Stokes can improve the system and how we can include viscosity and resistance forces. Other things to look into is physics simulations like COMSOL or OpenFOAM, which can simulate this as well. Though there's the question of whether looking into another programming language could benefit from this instead of using Python. Now lastly, ion production using Townsend discharge or other empirical data can help us predict how many ions are created during ionization. So there are many things to look for into this, but these are just some of the few we can massively improve the simulation to predict the best simulation and best system for our real-world applications on Earth. Thank you.